Welcome back to Honors Calculus. In this video, we're going to continue our discussion of continuity at a point with the idea of the one-sided limit. Get my head out of the way so you can see that title. One-sided limits are a tool of particular interest in functions that seem to change behavior drastically. And the place that that most commonly occurs is in a piecewise defined function. So certainly not the only place where one-sided limits are useful, but the one place I want to use as my example is where a piecewise defined function changes. So consider, for example, the function f of x equals x plus 1 if x is less than 2 and x squared minus 1 if x is greater than or equal to 2. For anything well smaller than 2, which is honestly anything smaller at all than 2, this function is well behaved. It's a linear function, f of x equals x plus 1. For anything larger than 2, this function is well behaved. It's a quadratic function, f of x equals x squared minus 1. At the point x equals 2 is where some weird things are trying to happen. So if we want to evaluate the limit as x approaches 2 of this function, we have to find a creative way of doing it. And the tool that mathematicians choose to use here is called the one-sided limit. The limit as x approaches 2 from the left of f of x to the left of 2, we are looking at x plus 1. And you can evaluate that limit and get 3, right? Right? The limit as x approaches 2 from the left of f of x is asking us to look at the things when x is less than 2, giving us that x plus 1. And the limit as x approaches 2 from the right of f of x is going to be the limit as x approaches 2 of the function we see on the right, x squared minus 1, which is 4 minus 1, which is 3. And when the limit on the left and the limit on the right agree with each other, that's when the limit of the function is defined and exists. All right, so that's the basic idea. Now that we have that in mind as a use case and how we're going to be using this, let's formally define limit from the left. Limit as x approaches c from the left, subscript or superscript minus f of x is equal to L. And we get that absolute value of f of x minus L is less than epsilon whenever opposite of delta is less than x minus c is less than 0. So this is 0 less than absolute value of x minus c is less than delta, and also x is smaller than c. And we can define the limit from the right basically the same way. The limit as x approaches c from the right, which we denote as a superscript plus of f of x is equal to L, means that for all epsilon greater than 0, there exists delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta. And in this case, we are looking at 0 less than the absolute value of x minus c less than delta and x bigger than c. All right, so this is a definition, not a theorem, but this definition is so straightforward that I'm still going to call it a corollary, saying that the limit as x goes to c of f of x is equal to L if and only if the limit as x goes to c from the left of f of x equals the limit as x goes to c right of f of x is equal to L. And you can see from the definition of limit from the left and limit from the right that we're taking the definition of a limit and we're just splitting up the cases of only look at x less than c, only look at x greater than c. So if you have it working for x less than c, you have it working for x greater than c, the limit already cuts x equals c out of the picture. So you have it working for everything. And again, there are a couple of other use cases that we're going to deal with, especially where functions are very badly defined. Right? The square root of x is undefined for x less than 0. So if you want the limit as x approaches 0 of the square root of x, it's not defined, but you can take a limit as x approaches from the right where it is defined. As you get more complicated square roots, you can make that more complicated and things can keep going from there. Limits from left and right are going to be very useful to us a little bit later when we start looking at limits involving infinite values, where the function goes towards infinity, and looking at values of x going towards infinity. One-sided limits there are going to be a nice way of straightening things out and trying to make sense of the nonsense that is infinity. But for our purposes right now, the big thing we're looking at is how these functions are defined, or how limits are defined for piecewise defined functions. All right, so let's take a look at the function f of x defined as 5x minus 4 if x is in the interval from -2 to 2, closed on the left, open on the right. And f of x is defined as x squared minus 1 if x is in the interval from 2 to 4, closed on the left, open on the right. And if I want to look at the limit as x goes to 2, we notice that that is a breakpoint in the function. And so we evaluate this using the left side and the right side. Right, the limit as x goes to 2 from the left of f of x is going to be the limit as x goes to 2. For things less than x equals 2, we're looking at 5x minus 4, which is 6. And if we're looking at the limit as x approaches 2 from the right, that's x squared minus 1, which comes out as 3. And because 6 and 3 are not equal, the limit on the left and limit on right do not agree with each other, we say that the limit as x goes to 2 of this function f of x is not defined. And let's wrap up with one more like this for you to try on your own. I'd like you to take a look at the function g of x, which is a piecewise defined function with 3 pieces. And we're going to be looking at g of x is 2 minus x. If x is in the interval from we're looking at 2 minus x if x is in the interval from 0 to 2. We're looking at x squared minus 1 if x is in the interval from 2 to 4. And we are looking at (15 minus 1 over x) if x is in the interval from 4 to 6. Looking at this function, I would like you to find the limit as x goes to 2 of g of x, the limit as x goes to 3 of g of x, and the limit as x goes to 4 of g of x. Notice that all of those intervals are open intervals, so there are some points where this function is not defined. Limits tend to not worry about those sorts of things. Take a few minutes, see where you can get to with this one, write out your solutions, and I'll see you in the next video.